Today we're going to continue our lecture on properties of solutions that we started last Wednesday. Remember though, today during discussion, I will be your discussion leader in discussion class today, so we can go over the exam, and then uh, which you weren't here, but that's okay. You can still go over the exam with us. So, um, the just remember though that since I expected, higher grades, that's okay though. We're gonna do for the rest of the semester. Every exam will have things on it that's about molecular orbitals. So it's good to keep yourselves nice and reviewed on that kind of stuff. There won't be a lot of questions. It'll be like maybe two or three. All right. So the last slide we talked about last time we were talking about properties of solutions. And this time we're going to continue that. And the last thing we talked about was organic molecules in water. And so when we were talking about those organic molecules in water, um, let me get my laser out here. We talked about how things that have a hydrogen bonding in it, right, will be soluble in water, for example. So for example, here we have two ethanol molecules, right? And they can do hydrogen bonding because we have oxygen there and a hydrogen there, an oxygen there and a hydrogen there. And they can do hydrogen bonding because oxygen is an electronegative atom and it does have lone pairs on it, right? And since ethanol is able to do that, we can get ethanol, um, we can get ethanol hydrogen bonding with water. And that's why ethanol is miscible in water, right? That's how we get our Everclear, which is like 95% alcohol, right? Or 190 proof, I believe, right? My favorite though is Captain Morgan. It's what is it? I think it's like 30% alcohol, something like that. Anyway, believe me, this is a good thing because if you were to drink just 100% alcohol and water wasn't like in there at all, you die. So there's this thing called ethanol poisoning, right? And if you just drank, a good few shots of 100% ethanol, you die, right? Or go blind. And the reason why that is because ethanol has this thing called an azeotrope. And what that means is that no matter what you do, when you're trying to separate ethanol out from water, there will always be 5% water left over, right? And that's why Everclear, right, is 95% alcohol, not 100% alcohol. I promise you anything that the manufacturers of Everclear, when they were distilling that alcohol from the corn, because they use corn when they do that, when they distill that, when they ferment it and distill it, right? They do the distillation process, and you can only get rid of up to 95% of the water. So you're usually left with 95% ethanol and 5% water, which is good for you. The only way, but when you go into like the chemical factories and you go into like our storage, I should go get one for you now. We do have 200 proof ethanol, which is 100 proof, 100% ethanol. So you might be asking yourself, how are you able to get it to 100? If all you can do is get to 95. Well, the reason why they can do it is because they'll added other organic ingredients like hexane or other denaturants, right? And I guarantee you, if you drink that, you die or you go blind. So hexane is not something you want to drink. Okay, um, and so you'll learn a lot about that during organic chemistry when you're talking about distillation and distillation apparatus. It's actually a lot of fun. So if we look at a molecule like this, oh, cyclohexane. Funny, I was just talking about hexane. Cyclohexane has uh, mostly, it's all not mostly, it is all CHs, right? A carbon and a hydrogen, carbon and hydrogen, carbon, hydrogen, carbon, hydrogen, carbon, hydrogen. So it's all nonpolar. It's all organic, right? And there's no oxygens or hydrogens. I mean, sorry, there's no oxygens with hydrogens on them, right? And so since it's missing those kinds of things, it's not going to be very soluble in water because there's not going to be it's actually not soluble in water at all, right? And so there's not going to be any hydrogen bonding between the water and the those CH groups, right? So for something to be soluble in water, you have to be able to do some hydrogen bonding with the water, right? Because remember, when you solvate something, the water is surrounding the molecule, right? Or surrounding the ions of the molecule, right? But if there's no hydrogen bonding, there won't be any surrounding it, right? But then when we look at things like sugar, this is glucose, which last time I called hexose, right? Or this is glucose right here. And you see that it's almost the exact same thing as cyclohexane, except it has OHs on it, right? The oxygen with the hydrogen. So it can do some hydrogen bonding, right? But notice that it has a lot more of these CHs than does ethanol does, right? And so it takes a long time to dissolve sugar in water, especially if the sugar, especially if the tea you're putting in is cold, right? You can put sugar in your tea and you can stir it while it's cold and it'll never dissolve. But you can actually increase the solvation effect, right, and make things more soluble in water by heating water up, right? And that's why when you make tea fresh and it's hot and you pour the sugar in, it dissolves almost immediately. Okay, so heat, temperature does have an effect on that. And so sugar, right, is soluble in water, but it's not as soluble like as ethanol is. And the reason why is because it has a lot more CH groups than ethanol does, right? But it still does have some of those OH groups, also known as hydroxyl groups, to do hydrogen bonding. So that's why it's like partially soluble in water. You could get it all to dissolve if you heat up the water, right? So talking again about miscible fluids or miscible solubility, liquid stuff, right? We know that if a liquid mixes together completely, right, then it's miscible. So ethanol and water are miscible with each other because when you drink a bottle of I mean, you shouldn't drink a whole bottle of Everclear, but if you're looking at a bottle of Everclear, you can't tell the difference between the ethanol and the water in there, right? It looks like it's all one solution, right? So that's called miscible. But liquids that don't mix, and I was just talking about hexane a second ago, liquids that don't mix are called miscible, right? And there's hexane right there sitting on top of the water, right? So quick question, which one's more dense? What? Water is more dense. Water is more dense because it's at the bottom, right? If you have a density that's less than water, you'll be on top, like oils, right? And then if you have a density that's more than water, then you'll be at the bottom, sinking, like a piece of lead, right? Don't forget your past lectures, okay? So hexane is very nonpolar. Water is very polar, therefore they're not admissible, okay? Not admissible. That doesn't make sense. That's a double negative. Therefore, they are immiscible. There we go. So I guess you could say they are immiscible or they are not miscible. All right? Both would mean the same thing. So, solubility and biological importance, right? There's many vitamins. Like you can actually look up on Google a list of vitamins that are both fat soluble, right? Because they're mostly nonpolar, and ones that are water soluble, like because they do have some hydrogen bonding capability, right? So here we have vitamin A right here. That's vitamin A right there. And holy mother, look at all look at all those carbons, and hydrogens right there, right? There's only one tiny little OH group right here. And if you didn't already know, a fatty acid looks like this. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I have one extra hydrocarbon there, but that's okay. The most common fatty acid that your body makes through the fatty acid synthase pathway is called palmitate, right? And it's a 16 carbon fatty acid. I think I have 17 on there, but that's okay. The point though is that look at all the CHs, right? If you do, oh, I guess I never even said that before too. Um, if you don't have anything attached to the carbon, absent anything else like a charge or a lone pair or something, it's always assumed that those are hydrogens. Did you guys know that? And the reason why they do it that way is because it takes a lot of time to draw out all these hydrogens, and so on, right? So this fatty acid here, right, has a very long chain of carbons and hydrogens, and so does this vitamin A right here. Very long chain of carbons and hydrogens, just a tiny little OH there. So these guys here are going to be soluble with each other, right? Vitamin A is soluble in fat. But taking a look at vitamin C, which is also known as ascorbic acid, I believe, right? Isn't vitamin C the thing that keeps you from getting scurvy? If you didn't know this, back in the day, so I'm a huge fan of like the Pirates of the Caribbean franchise as well. And one of the things that they used to make pirates and sailors do a lot is eat lemons or limes, right? And so they would call old faring soldiers back in the day, like in the 17, 1800s, limeys. And the reason why they called them limeys is because they were feeding them limes. And the reason why they were feeding them limes is because you get vitamin C from limes. And the reason why they did that is to prevent them from getting scurvy, right? Does anyone know what scurvy is? It does make you ugly. But specifically, it makes your gums bleed, right? Specifically, it makes your gums bleed, okay? It affects a lot of things, but the most visual thing is that it makes your gums bleed, like really bad, right? So they didn't want their sailors or their pirates, their first mateys, right, to be all scurvied, and so they called them limeys because they were giving them limes. Make sense, right? And so taking a look at vitamin C here, right, we can see that vitamin C has a lot of OHs, right, that can do hydrogen bonding, and then there's not as many carbons and hydrogens, and so that's why it's water soluble, right? That's why it's water soluble. Excuse me. So your first question for today is this: which of the following molecules is most fat soluble? Which of the following molecules is most fat soluble? And you should recognize this molecule right here. I've talked about it a gazillion times. And also keep in mind too what a fat looks like. Remember, it looks like this. Did I miscount again? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I always do that. That little guy right there, don't worry about that little guy right there. Okay? Don't worry about that one. That little guy. So another franchise I'm a fan of is the Super Troopers franchise. Have you ever seen the movie Super Troopers before? It's a good time, right? And they're like at the shooting range and they're shooting at each other and one bullet goes stray off and doesn't actually hit the target. Like there's a hole over here, and the guy's like, "Oh, that little guy. Don't worry about that little guy." Right? So this should be 16 carbons here. So for that little guy right there, don't worry about that little guy. Okay? But that's what a fatty acid looks like. The most common fatty acid. Okay. I'm impressed. I'm very impressed. How many people are in the room right now? 10? I think there's 10. Yes, there are 10. There are 11. Holy crap. Terrible. I'm terrible at math. Wait, how's there 11? 6? Oh, there's 11. 5 plus 6 is 11. Why didn't you guys tell me that? Okay. So here's the answer. Here's the scores, and it's almost half and half. Not really. Most of you got it right, though. I'm very proud. Right? The answer is A, and the reason why the answer is A, right? The reason why the answer is A is because of this. The reason why. Oh, here it is. The only two things that have like the long carbon chains, right, of CHs are with the fatty acid is molecule A here. This is water, of course, doesn't have any carbons. While this one does have carbons, look at all the hydrogen bonding capable functional groups here, right? So that's definitely going to be soluble in water. So the only one that is going to be soluble in fat, or mostly soluble in fat, is going to be the top one here. Does anybody know what that molecule is? You use it every day, especially now. right? With the pandemic and all that, trying to keep clean. Yes, it is soap. This is sodium dodecyl also known as lauryl sulfate, right? It's in your shampoo, it's in your hand soap, it's in anything that makes your soap like suds, bubbles, right? It's in your Dawn, right? So I cooked a brisket yesterday, or I smoked a brisket over the weekend, right? And when you're smoking a brisket, the fats from the brisket render out of the brisket, which makes it so good. That's like the best part of a brisket, all the fatty stuff. But when it renders out, it falls to the bottom of your smoker, and now your smoker's like covered in fat, right? And the only way to clean all that up is to shoot a whole bunch of Dawn in there, right? Because Dawn breaks through the fats, just like they say in the commercials. It's the same reason why they use Dawn to clean up oil spills on animals, right? Their little picture of their little duck is like the cutest thing ever. Getting a bath with Dawn. I even if you didn't know this, I have 3 dogs, and I actually bathe all 3 of my dogs using Dawn dish soap. Like I don't even use the shampoo from the pet store, because if SeaWorld can use it to clean like baby whales and dolphins and birds, you can use it on your dogs, huh? Yes, that too, right? Well, actually, soap actually, just water will make the fleas jump off of your dog, right? Because fleas don't like water, number one. So if your dog has fleas on them and you put them in like a pool, you'll see this little pool of fleas floating away. Yeah, so that's why you give your dog a bath outside, right? But then, huh? Yeah, it does. So the water doesn't actually kill the fleas, but the Dawn soap will kill the fleas. Yes, Dawn is amazing. So you shouldn't waste your money on like those expensive dog shampoos or cat shampoos. Literally, just use Dawn. It's like the best thing to use on animals, right? Because it's pure. It's like it literally is. Other than the blue food coloring they put in there, right? I mean, it could be green. I've seen red too, right? It's all sodium dodecyl sulfate. It's all good. All right. Next thing. See, not only are you learning chemistry in this class, you're also learning life lessons, right? Things to do at home, right? Okay. And I don't know if you noticed this too, but like for some reason, other dish soaps just aren't as good as Dawn, right? They're just not as good. And I mean, it might be just because they have so much more sodium dodecyl sulfate in it, right? It always says like 4x concentrated or something. That helps. That really helps. Okay. All right. Oh, the other thing good about Dawn too is it doesn't have a lot of like fragrances, right? It doesn't smell like perfume like some other soaps do, right? It has a good smell, but it doesn't like smell like perfume, so it won't irritate your dogs that way either. Okay, off topic. Pressure effects. Okay, the solubility of solids and liquids are not appreciably affected by pressure, which makes sense because um, if a solid is a solid, right? Like it's like a salt crystal, and you throw it into the water and it dissolves. It doesn't matter what the pressure is, right? The water is still going to dissolve the salt, right? So that's what it's saying there, where it says liquids and solids are not appreciably affected by pressure. But the thing that is appreciably affected by pressure is gas solubility, right? So what's a really good example of gas solubility that you can think of in your lives? It's a thing I have to give up because I found out that I have to take my Texas Wesleyan official portrait on October 4th. So I need to lose some weight before I get into my suit because I don't fit in my suit right now. So it's the thing I have to give up. Soda, exactly. Soda is the example, right? Because what is soda? But carbon dioxide pressurized into some sugar water, right? That's literally what soda is. It's carbon dioxide. Why do you think when you crack the can open, it goes because the can's under pressure, right? The can is under pressure. What pressure is it under? A crap ton of carbon dioxide, right? So the more pressure there is, you can and actually a funny thing, the answer was in this picture. Right? This is a bottle of Sprite. So, but being from Texas, from Houston specifically, we called everything Coke, by the way, right? And then I went to Alabama. There they call everything pop, and like, what's pop? Just give me a in Alabama too. Well, I was in northern Alabama, so near the Appalachian Mountains, so maybe that's why. You know, some people call it cola, not Coke, but I know I always called it Coke. And so there, I once asked at a restaurant in Alabama, can I get a Coke, please? And they actually brought me a Coke. They didn't ask me what kind of Coke. So I was like, why are you giving me a Coke? Why didn't you ask me what kind of Coke I wanted? But I wanted a Dr. Pepper. They have Dr. Pepper out there, right? But yes, it's a very weird thing. Okay. Us? Have you never noticed that? Like everybody calls soda here Coke. Oh, I'm totally used to that. I'm totally used to saying I want a Coke, and they say, okay, what kind? And I'll say Dr. Pepper. At least that's the way it was in Houston. So I haven't lived here in DFW for that long, so maybe it's different up here. But in Houston, everything is Coke, which is crazy because Dr. Pepper really is the big thing in Houston too. So you think everybody would be saying, "I want a Dr. Pepper," and then asking for something else, you know? But that's harder than saying Coke. So there's this thing right here called Henry's Law, and Henry's Law says that the solubility of a gas, right, is proportional to the partial pressure of the gas above the solution. Okay. So here's the equation, right, and here's solubility of the gas, and this is the partial pressure of the gas. K is just a rate constant, and all you really need to know is that both of them, right, are on top. They're both numerators, okay? Not one is just a quick, just in case you didn't know. Whenever you see a number by itself like that, it's always a number over one, right? Otherwise, it's the other way around. It's a fraction. So if P were down here where the one is, then it would have an inverse relationship, right? But since P and S are both on top, that means that it's a proportional relationship. And that is borne out when you look at this graph right here, right? As the partial pressure of helium increases, right, the solubility of helium increases. As the partial pressure of hydrogen increases, the solubility of nitrogen increases. The solubility of nitrogen increases. And then here's carbon monoxide, that solubility increases too, and so does oxygen, right? So does oxygen. So thinking about this all conceptually, right? Generally, and you've seen this slide already before, right? But when you have it just sitting there and there's like normal pressure above the solution, right? And then there's a solution, the gases are passing back and forth, that's called equilibrium, right? When the amount of gas that is being dissolved is the same rate, the rate of the amount of gas being dissolved is the same rate as the amount of gas not being dissolved, right? It's called equilibrium, okay? But you can push it down, right? And make a lot of pressure in there, right? And then put a lot of pressure in there. When the pressure is increased, the more CO2 dissolves. So now the rate of CO2 dissolving in water is higher than the rate of the CO2 coming out of the water, right? And that's how you make a soda, okay? That's how you make a soda. Or I guess a Coke, since I'm from Houston. And then if you pull it the other way, right? Oh, sorry, it doesn't show the other way. But eventually, when you get done with that, right? It normalizes out, and now you have a new equilibrium, and that's inside your Coke can right there, where you have uh, no more change in the rate of dissolving and undissolving, right? But the picture that's not shown here is what if you pull the syringe out, right? You make it less pressure in there. More stuff will come out of the solution than go into the solution, right? Have you ever done that with a syringe before? Have you ever like kept accidentally maybe left the lid on a syringe with a solution inside the syringe and tried to pull the plunger? What do you see? You see bubbles come out, and that's because you're creating a vacuum, which is a lower pressure, right? And that's quite literally pulling all those gas molecules out of the water or whatever you had in the syringe, right? And so that's why you've got to flip it upside down, tap it a little bit, click it a little, like hit it at the top, and then squeeze out all the air, right? Because you don't want the air going to a person, because then you can cause them to have an air embolus, right? And then they'll die. And you don't want that, do you? Air emboluses are bad, right? If you don't know what an air embolus is, it's quite literally an air bubble inside one of your blood vessels. It blocks the blood vessel, and blood can't get by, right? And imagine if that went into your coronary artery, right? It'd give you a heart attack the same way that a clogged artery would from fat, right? So this is why we do things, right? It's not just because on TV it looks cool to tap it at the top of the syringe, and squeeze it all out, right? There's a reason why we do these things. But I bet you never thought about it that way before. Okay, and I've already talked about this a couple of slides ago, but you should know me by now, where I tend to jump the gun and start talking about things before it even gets to the slide, right? But temperature has an effect too on solubility. So interestingly enough, right, like I was saying before, when you're talking about solubility of a solid in a liquid, as the temperature increases, the solubility increases, right? Just like I was talking about with tea. Cold tea will not dissolve as much sugar as what? Hot tea will, right? And that's because the hotter you get it, the more soluble that solid gets in the tea water. Okay. But on the other hand, look at this. As temperature increases, right? Turns out the solubility of the gas decreases. Someone give me an example of that. Say again? Tea? What? Oh, give me an example of when you increase the temperature, right, and the solubility of a gas decreases. Say again? No, water, even though water is evaporating, when you're talking about things that are dissolved in water, it's usually like oxygen, right? And yes, it's true, warmer water has less oxygen in it because oxygen isn't as soluble in water when it gets heated up, right? So have you ever jumped into a pool that was like really warm and it doesn't feel as nice? And the reason why is because the thing that actually makes you feel nice in there is that there's all these air, like, there's all this oxygen dissolved inside of the water, right? But if it's a really hot pool, right? Unless it's a heated pool, then it's awesome because you're not going to get into a heated pool unless it's cold outside, right? But that is true with oxygen. The one example that will probably be the most relevant to you is how many of you have left your soda sitting out in the heat before? What happens to it? It goes flat. Does it not? No more bubbles. Why is it no more bubbles? Because you heated up the cola, the soda, the Coke, right? To like room temperature from when it was like cold in the refrigerator, right? And then all the CO2 just is not as soluble anymore. It comes out, it bubbles out, and it's not the soda's flat. Does that make sense? Right? It's crazy. Absolutely crazy. Oh, another good example too with the water. Have you ever drinking water and it feels flat before? Like, if you drink some water, it feels flat. Usually, when you drink water and it feels flat, it doesn't feel as tasty. It's because all the oxygen has been like come out of the solution, right? There's no more dissolved oxygen. But what you can always do, if you were so inclined, all that dissolved air that's gotten out, you can put it back in by putting a straw into your water and blowing bubbles in it, right? And it will actually become less flat. That being said, the temperature effects have the uh, have the upper hand here because your water is still going to be room temperature, right? So the Coke goes flat in the heat because gases are less soluble in liquids at higher temperatures. That's what that graph is saying. Well, I mean, it makes sense because think about it, as you're heating something up, right, and it's a gas, you're making more interactions, collisions with the molecules. They're all bouncing off of each other, hitting each other a lot more, right? And the gas was already like forced in there anyway, right? And so if you heat up a solution, it's going to knock all those gases out. No, because was the CO2 ever liquid inside of your Coke? No, I promise you would not be drinking liquid CO2 in your Coke because liquid CO2 is like negative 78 degrees Celsius. right? Your Coke would be frozen if it was liquid CO2. The only evaporation that occurs is the water that's in the Coke, right? It gets undissolved. Yeah, that's not like a specific term for it now. It just becomes less soluble, right? But no, there's no water is absolutely getting dissolved. I mean, not sorry, not dissolved, evaporated. But that's not what's causing your soda to go flat, right? Indirectly, it is because the only reason why the water is evaporating is because it's getting warmer, right? But it's because the warmness is causing more molecular interactions, right? With a gas molecule that doesn't already want to be in there. It had to be forced in there by higher pressure, right? And so now you're creating even more pressure in the liquid by heating it up. And so the water molecules are knocking back and forth, trying to evaporate themselves. And in the process, the thing that was pushed down to be in there in the first place with the pressure is just going to get released, right? But that's definitely not called evaporation. You have to go through a phase change to get evaporation, okay? And if you have to use pressure to put something into something like that, like CO2 into the liquid, the Coke like that, right? It's still a gas. If it wasn't a gas, why would the Coke be bubbling when you open the Coke, right? What's that bubbling? That bubbling is literally CO2 gas, right? Does that make sense? Any other questions? Yes. Say again?
It says for most solids,
Mm-hmm.
but is it solids and liquids?
Yeah, well, it really depends on the liquid. It's mostly for solids, right? Because some liquids are really, uh, some liquids are high volatility, and so even though you can't make a general statement about liquids, right? But you can make a general statement that if you put salt into water, right, and you heat it up, more salt will go into that water. Just like I showed you with the sodium acetate, with the one I got in trouble for cussing about the heating pad, the Wonder Packs heating pad thing, right? When I clipped that little thing and turned into a solid. Remember the orange thing, right? You can definitely do that for most solids. Like you can heat up water and you can put in like some kind of salt or some kind of sugar or something, right? And it will make it so that's more soluble, right? And you can put more into that liquid. But that's not true of every single liquid. That's why that's not up there. So right now, just for this slide, right? Just for this slide, just know that for solids in liquids, right? As you heat it up, the solid is more soluble. And for gases, as you decrease the temperature, as you increase the temperature, the solubility decreases, right? One is a relationship in which one goes up, the other goes up. That's solid into liquid, right? But then gas into liquid, right? It's the other way around. One goes up, the other goes down. Does that make sense? All right. Next question. What phase of matter does pressure have the most effect on in terms of solubility? Whew, I'm already getting tired. Let's see here. So far, so good. There's two more people. There's two more. There we are. Okay. So I'm happy to say that the vast majority was paying attention to the last slide, right? Because the answer is, in fact, C. the phase of matter that has the most pressure, that has the most effect on, with pressure, is definitely a gas, definitely not a solid, right? So whoever's put solid there, make sure you're clear on that before the next exam, okay? But it's definitely pressure has the most effect on a gas, right? Has the most effect on a gas. All right, so whenever you're talking about solutions, then, and we're talking about things dissolving in solution, right? We have to talk about the solution's concentration. And I just changed the slide, and I forgot to change the screen. Hold on one second. There we go. Okay, so solution concentration. We have discussed solubility and solutions qualitatively, right? And so there's this thing called qualitation, and which comes from the word quality, right? And then there's this thing called quantitation, which comes from the word count, right? So quality or qualitatively, it means talking about it like conceptually, thinking about it like in terms of the materials itself, right? Whereas quantitatively means that we're talking about things in their numbers, like how soluble something is with a number, or what the concentration is in there, right? So for example, I can say that I have a salt solution, but how much salt is in that solution? That's quantitation, right? So now we will give specific amounts to each of the solutions. Okay, and the way we do that is with several different units of concentration. Okay, we have the percent mass, and that's generally um, things like grams per volume, volume per volume, grams per gram, right? We have parts per million, right? Which parts per million is um, the number of molecules for every 1 million molecules, right? And then parts per billion is the number of molecules for every 1 billion molecules, right? And then we have the mole fraction. Mole fraction is we've talked about that one the most, where like, if you have it on a scale of 1% to 0% to 100%, what percentage is the solute and what percentage is the solvent, right? That's the mole fraction. And then the two that we probably use the most in chemistry, like a lot of like the environmentalists, the biologists, I think the biologists use like mass percentage all the time. They're always about grams per mil and stuff like that, right? And then environmentalists like to use parts per million, parts per billion when they're talking about like the amount of greenhouse gases in the air, that kind of thing, right? Chemistry, we use molarity and molality the most. Okay, molarity and molality the most. Okay, and we'll go through each one of these individually. So let's do our next question. Which of the following is not a unit of concentration? 8 responses so far. So far, it looks like everybody's paying attention. Hallelujah. Hallelujah. One more person. Still waiting for that one more person. There we go. Hallelujah. Everybody was paying attention because all 3 of those were units of concentration. Okay? So let's go through each one by one. Okay, so the first one we're going to go through is going to be percent mass percentage, right? So in mass percentage, right, percent means out of 100, like I was saying before, and then so you can take the ratio of the mass of the solute to the total mass of the solution, right? And then you multiply it by 100 to make 100 to make it a percent, right? So like I was saying before, the biologists always like to go like grams divided by mils, right? So the mass of for example, up here, it would be how much mass of salt there is, right? And then the total mass of the solution afterwards, okay? So you'll hear them say things like 1.0 grams per mil or something like that, right? But you can also do uh, 1 over the solution, and times it by 100 and get a percentage out of it. Now, we very rarely ever use mass percent in chemistry, but as you go through your chemical careers, or your careers as scientists, you'll have to go look at papers from other disciplines, and you'll see this a lot in like the life sciences, right? In the life sciences. I mean, and I mean, I don't blame them. It's easy, right? Just weigh out the mass of what you want and put it in the solution you want, right? The next one, okay, is sorry, parts per million and parts per billion, right? This is still relating the mass of the solute to the total mass of the solution, right? And so since the percent is out of 100, we multiply it by 100. Parts per million, we'll multiply by 6, right? And if it's parts per billion, it's multiplied by 10 to the 10. Sorry, let me say that again. Parts per million, we'll multiply it by 10 to the 6. Parts per billion, we'll multiply by 10 to the ninth, right? So just as an example here, we would have parts per million of a component, means the mass of the component divided by the total mass of the solution, okay? And then you'll get the times 10 to the 6, and that would be your parts per billion, right? And or parts per million. And the reason why you do the times 10 to the 6 is because that's per million, right, molecules, right? Or here it's per billion, right, molecules. That's why you have to do the 10 part. But again, we don't use this a lot in chemistry. You'll see it sometimes in chemistry, but again, it's just mass of the component in the solution, like the solute, then the total mass of the solution times the either 1 million or 1 billion, right? We'll see this sometimes in chemistry, especially if we're looking at a graph, right? The mole fraction, right, is literally the moles of the component divided by the total moles of all the components, right? Okay, so mole fraction is pretty simple. The mole fraction is a ratio of the moles of the substance to the total moles of the solution, right? Um, it does not matter if the solute, if it's a solute or a solvent, right? So that's your mole fraction. But then the ones that we use the most, and the ones that I will test you on the most, are these two right here, right? One is called molarity, which you'll see all everywhere. Like if you go into our chemistry in our chemistry stockroom right now, every single chemical in there is labeled as something something molar. Okay, every single thing in there. Okay, and so molarity is literally the number of moles of solute divided by the liters of solution, right? So we'll say like a 1 molar solution of uh, of sodium hydroxide, right? Uh, or I can't remember what the molarity of concentrated hydrochloric acid is. It's pretty high though. I can't remember. I won't tell you something wrong because I can't remember what it is. But anyway, we use molarity a lot, right? And so generally molarity is again moles divided by a solution, liters of solution, so a volume here. And so it'll always be L, one big L here, okay? And then molality, right, is basically the same thing, but instead of moles, liters of solution, it's actually kilograms of solvent, right? Kilograms of solvent. Okay, it's kilograms of solvent. And honestly, we do molarity a lot more than we do molality, right? But you'll still see molality a lot. Okay. So a quick note about this, right? A quick note about this: molarity versus molality, right? When water is the solvent, the dilutions, the dilution, the dilute solved solutions will have a similar molarity and molality. Can anyone tell me why? When the solvent is water, the number you get for a molarity will be very similar to the number that you get for molality. Why is that? What's special about water? And don't just say it's a universal solvent.
Is it because density is like one?
That's exactly right. That is exactly correct. Good job. That is exactly right. Since water's density is 1, right, it means 1 liter of solution is pretty much the same as 1 kilogram of stuff, right? Remember what the thing was here? See, liters of solution, kilograms of stuff, right? So solvent. So 1 mil is pretty much the same as what? 1 gram of water, right? If you have 1 milliliter, if you have 1 milliliter of water and you weigh it, how much does it weigh? 1 gram, right? Because the density of water is what? 1 gram per mil, right? So if you have a liter of water here and you have a kilogram of water here, it's the same thing. They're pretty much the same thing because the density of water is 1. Does that make sense? But if it was anything else, it wouldn't be the same. Any other solvent that has a different density than water, it wouldn't work, right? But if the solvent is water, then most these numbers will be very, very similar. The only reason why they're not exactly the same is because though we accept that water's density is 1, water's density is actually like 0.999999585 or something like that, right? But it's pretty much 1, and that's why they're very similar. Okay. Okay. Molality does not vary with temperature because mass does not change, right? When you heat something up, for example, if I were to heat up this table right here, right? If I heat up this table right now, I feel like it's like 95 degrees in this room because I'm like sweating like crazy, right? But if we heated it up to like 212 degrees Fahrenheit and we boiled this table, right, in like hot air, like an air fryer, would the mass of this table change? No, no, not at all, right? Not at all. And that's why molality doesn't vary with temperature because mass doesn't change, right? But molarity does vary with temperature. Why does volume change when it's a liquid and you heat it up? Remember, right? Liquids expand when you heat them up, right? You're putting more energy into those liquid molecules. They're bouncing around and they expand, right? So much, in fact, that eventually they'll do what? They'll evaporate, right? And that's why molarity does vary with temperature. So oftentimes, when we're talking about molarity, it's always going to be at room temperature, 25 degrees Celsius. That makes sense? Okay. Carol, I'm very proud of you, though. I'm so glad you got that. Good job. I'm so glad you got that. Okay. Next question. Why is molarity and excuse me, why is molarity and molality similar when water is used as a solvent? Your classmate there has already answered this question, so I better see the same answer for every single person, and it better be the correct answer. Now, Kiara, if you get this wrong, then we have a problem. You were the one that answered the question to begin with. Whew. You having trouble scanning, Vanessa? You know what I could do? I could bring like an extension cord, and just like put it right here with like a power strip so everybody could just plug in their laptops. That way you don't have to sit over there by yourself. It looks like you're not engaged, but in fact you're actually are engaged. So yeah, I'm doing this low carb diet thing, so hopefully I lose some weight before October 4th. I have like a week, right? I've already lost 4 pounds since yesterday. Yeah, exactly. It is how it goes for guys. It's tough being a woman. My girlfriend said the same thing. She's like, "You stop drinking soda and stop eating bread for 2 days, and you've already lost 4 pounds." I'm like, "Yes, I'm sorry." A loaf, a whole loaf? I'm not surprised. If you're an athlete, you probably need a lot of carbs. Well, bread is healthy, except that it's got a lot of carbs. So, okay, okay, okay. I just have to ask: Am I being punked here? Like literally, am I being punked? Like how is it possible that someone got this wrong? I did say that's not why. I literally said, don't tell me. I literally said the words, don't tell me it's because universal water is a universal solvent. And then Kiara answered the question exactly right. She said it's because of the density of water. And then this question came up. Huh? Maybe what? Okay, so whoever got this wrong right here, do not get this wrong on the test because I will be super pissed. Okay? I will be super pissed. This is like a fundamental thing. Okay? Fundamental thing. All right. We're doing really good on time. That's great. Okay. All right. So next we need to talk about colligative properties, right? And colligative properties are basically the thing I was talking to you about before. Um, I always allude to things before we actually get to it in the slides, right? But colligative properties are things that depend on the quantity, not the identity of the solute particles, right? And so among colligative properties are the vapor pressure being lowered, the boiling point being elevated, the freezing point being depressed, or the osmotic pressure, right? And so a good example of boiling point elevation is, again, we'll use salt water as our example, right? If you add salt to water, right, it actually makes the boiling point of water go up. The water doesn't boil as fast. It needs more energy to boil, right? So oftentimes people will add salt to their pasta solution, right? Their pasta water, and and it does help with like the bubbling over of the water when you're cooking pasta, the bubbling over. But why is it actually helping with that? It's helping with that because I bet you no one really knows why putting salt into pasta water keeps it from boiling over. Exactly. The salt increases the boiling point of the water, so you don't get as many bubbles. So vapor pressure, right? What was it? Vapor pressure depression, right? It was what it was called. Vapor pressure lowering, right? Vapor pressure lowering. And we talked about this before, right? Because of solute-solvent interactions, intermolecular attraction, higher concentrations of non-volatile solutes will make it harder for the solvent to escape the vapor phase. Therefore, the vapor pressure of the solution is lower than that of the pure solvents, right? So this is basically the other side of saying that the boiling point gets higher, right? The reason why the boiling point gets higher is because the vapor pressure gets lower, okay? And so um, therefore the vapor pressure of the solution is lower than that of a pure solvent. So looking at this right here, we have equilibrium, okay, and we have the same. You see these arrows right here; they're like the same shape and the same size. And the reason why they're the same size is because there's an equal amount of gases. Sorry, there's an equal amount of molecules becoming gases and then going back into being a solvent, right? Going back into being liquid. But then right here, we can have this thing where the rate of evaporation is reduced by the presence of non-volatile solute, right? So non-volatile solute is something like salt. Salt is non-volatile, right? Just a quick review, volatility doesn't mean explosive. It just means it has a low boiling point, right? But salt doesn't have a low boiling point, right? You can't even melt salt until you get to like 1800 degrees, right? And I don't even remember I might even be wrong about that, but I don't even remember what the boiling point of salt is. Probably in the 3000s, right? And so when you add some salt to it, right, it actually makes add some salt to the solvent, right? It makes the vapor pressure lower. So now less molecules of for example water are becoming a gas. More molecules of water are becoming what? A liquid, right? So it's literally the opposite, not the opposite, but the other side of saying it increases the boiling point, right? Because adding salt to water will increase the boiling point, but it will also do what? Lower the vapor pressure. Does that make sense? And both those things together make it so that your water doesn't boil so quickly, right? At a low temperature, so that your pasta, right, water doesn't boil over. Okay? But then, of course, eventually everything is reestablished in equilibrium again, right? And now the rate of evaporation is the same rate as condensation. Okay. So that's vapor pressure lowering. There's this thing called Raoult's law, okay? And Raoult law says that the vapor pressure of a volatile solvent over the solution is, so the volatile solvent over solution is basically if you have like a pot of water and then above that pot of water is a whole bunch of water vapor, right? And so that's the volatile solvent is the vapor, water vapor on top of the water when you're boiling it, right? Over the solution is the product of the mole fraction of the solvent times the vapor pressure of the pure solvent, right? So here we have the mole fraction right there, which is X, right? And it's multiplied by the vapor pressure of the solvent right there, and then you'll get the, I lost my train of thought. The vapor pressure. You'll get the new vapor pressure after you do that math, right? The vapor pressure of the whole solution. So I don't know if I'm going to ask you a lot about. I'll ask you a lot about like the relationship, but I'm not going to actually make you do the math for that. I mean, it's easy math, multiply this, multiply that, divide that. But I care more about you understanding the concept right now. Okay. Ideal solutions. In ideal solutions, it is assumed that each substance will follow Raoult's law in the mixture. Well, in a mixture. All right. So which of the following is a colligative property? Which of the following is a colligative property? Colligative property. See, this is great. I always get so happy when all the colors are the same. All the colors are the same. So I get so happy. Thank you very much. Still waiting for one response. Oh no, not one response did it wrong. I'm just kidding. I'm just joking. Everybody did right. Right? This indeed is, every one of those is a colligative property. Okay? Every one of those is a colligative property. Good job. Good job. See, the other reason why it makes me happy that we all get the right answer is because number one, we don't have to turn around and discuss it, right? But then number two, it means you're paying attention in class. Okay? And nothing makes me happier than students paying attention in class because I think I'm an awesome lecturer, right? So not to toot my own horn or anything, but I think I'm an awesome teacher. So you need to pay attention. You'll be very, you know, be very sad when you don't get me as a teacher. Just saying, right? Okay. When you have another teacher and they're not as cool as I am, it's gonna be a very sad day for you. Okay, so here is us talking about now the boiling point of elevation. Remember, adding salt to water makes the boiling point higher, so your pasta water doesn't boil over, right? And so if you take a look at this here, right, this is the normal, this is just like a generic solvent, right? We can call it water if we want to, right? And the normal triple point for the solvent is here, right? And so this line here is the solid to liquid. This line here for the condensation and the melting. Sorry, not condensation, melting and freezing. And then here's the line for condensation and evaporation, right? And here's the line for sublimation and deposition, right? And so the black line is the normal triple point for this generic solvent. Say it's water, right? But when you a add in a solute like salt, right? Everything changes, right? Now we have the solution point moving over, right? It's no longer here. Say that was 100 degrees right there for water, right? The blue line is now the new triple point, and when it's lower like this, it makes it so that the boiling point now is here, right? So instead of it being 100 degrees for water there, it could be like 120 degrees for water. Does that make sense? Right? Notice it doesn't just affect that too. It also affects the melting point, freezing point too, right? If you've never done this before, you can actually add salt to water, right? And someone already said this before, someone who stole my thunder a second ago, right? You can add salt to water, it'll keep the freezing point of water lower. So when we have big freezes like we do, I need to do some exercise too. Let's stretch out. Yeah, okay. I just popped my back. That's crazy. Um, did you? um, so when we had that big freeze in February, right? We had that deep freeze in February. You know, barring the fact that we couldn't go anywhere, there were trucks out there putting salt on everything and sand, trying to melt the ice, right? And usually it does work. Sometimes it doesn't, right? Because it's just so cold, and salt isn't enough to maybe depress that boiling point. I mean that melting point a little lower, right? Because we went way below zero, right? We were at like -20 or -30 during the freeze, right? Um, was it that cold? I just remember it being very cold.
It was cold enough to be inside. And life wasn't.
13 degrees? Oh, sorry. When I say -20, 30, I meant in Celsius. But yes, yes, it was like 13. Yeah, I forget that the meteorologists use Fahrenheit, right? But yeah, it gets super cold, and if it gets that cold, the salt wasn't good enough, right, to bring it down enough. Because you can see here, you add in the salt here, right, and it only moves the boiling point. I mean, the melting point that much, right? I don't know how much it is. I haven't done the experiment to know, but it does. And then the last thing we'll talk about today is freezing point depression, right? Which is the same thing I just talked about, right? And Oceana, they're stole my thunder about, right? Here, we are having the new blue line here makes it where the freezing point now is much lower temperature than it was before. Make sense? Right? One graph, be sure to be able to tell the difference between the two, right? One plot here, one triple point and phase diagram here shows how the blue line with the solute in it gives you a higher boiling point, right? And then this one shows you, the blue line gives you a lower melting point, okay? So adding salt to water does two things, right? What are those two things? Increases the boiling point, and does what else? Decreases the melting point, right? And that's it for today. I will meet you guys in the next room to go over your exam.